Next in our grounding, I'd like to talk about opcodes or instructions. The processor knows, I think it's 266 instructions, and those are, add, divide, subtract, increment, move a byte from memory to register, swap registers, perform an interrupt, so on, so on, so on. This processor and ones like it, older ones that is, newer ones for some reason seem to have moved away from this, which is completely idiotic because it makes sense to me, but I digress again. They have for instruction 0, opcode 0, no op, no operation means do nothing. Now we're going to convince the processor that it's receiving no ops every time it tries to do a request. And the way we're doing this is that we're going to force the bus to always have a no op on it. Remember, these are active high, so we have tied all of the 8 data bits on the data bus to ground. So every time the processor hits the data bus to see what instruction is waiting when it's done a fetch, it will find everything set to 0, and 0 gets decoded as a no op, do nothing. One of the things I've done with this circuit is to illustrate what it's doing. I have, since there's nothing else to see here, I've taken the least 4 bits of the bus and tied it to the LEDs. And this means that every time it tries to assert an address with one or all of these 4 bits on the bus, it'll light up. This is helpful. Now usually when the processor is running at full tilt, even at 2.5 megahertz, these lights would be flashing like mad. And that's obviously too quick for us to see, so we needed a slower clock source. Now the original design that Tom Shearer had a JK flip-flop and a capacitor to produce a very slow clock, 28 hertz. Not even like kilohertz, but 28 hertz, 28 cycles per second. And the way it worked is, I have a design of a flip-flop somewhere here. And this is a stepping circuit, or like this circuit here, but you would have the capacitor, and the capacitors, basic electrics here, they store up a charge, and then when they fill, they fire, and they store up, and they fire, and they store up, and they fire. Now in the case of this, what we're doing is we're using it to smooth out the regulated power, but in the case of the clock, every time it fires, that would be a change in the clock line, whether it's high or low. And then you use the JK flip-flop here to smooth out, to debounce, which we'll get into in a second, that signal. Now, I couldn't make it work for the life of me. Now, I'm confident that the design was fine and that I'm just inept. I think that the cap that I pulled out of my parts bucket was probably bad. I don't know if you guys do it, but God knows you've seen my sheds, so you know what I collect like. I have a habit of taking old boards and melting the solder on them and smacking it against the desk and popping the components off, which is where I get things like this. And then I've got a little container bits and pieces here. Now that's handy when you have, random caps that you need. Now in the case I needed I think this is 1 nanofarad cap, and it just didn't work, so I decided to move on to this circuit here, which is also helpfully provided. And this is a hand-stepping clock source. Now, most processors, you can't do this. I'll explain why in a second, but the clock source needs to be clean. A good, clean clock source. Look, another diagram. It looks like this. So you go high, low, and so on, however many times per second. And the transitions from high to low to high to low is what gives us that hertz frequency, like our 2.4 gigahertz processors are going from high to low states, 2.4 million times per second, or no, 2.4 million, that'd be 2.4 megahertz, so 2.4 billion times per second. This is a clean source. It has a nice clean line when it transitions. What happens if you use a switch as a clock source without any kind of debounce circuitry is you get what's called ring or ripple. And it looks kind of like this. As it transitions high, it kind of bounces for a second and then it stabilizes. And this happens in the case of a switch like this because as you're going from one contact to the other, there's that microsecond where the contacts aren't quite touching or they're still in motion, and so it's not a clean voltage that goes across it, so it rings like this and then down on the other way. Well, that's no good. That confuses the hell out of the processor. We can't give it that kind of signal, so we use our flip-flop to latch those signals in, which is extremely helpful because what happens is then when we flip our switch, it will latch either the rising or lowering edge and hold it. And because it's done in TTL logic, it's almost instantaneous, which gives a nice, clean, segregated clock. So we flip, it'll change from low to high almost immediately. When we flip back, it'll change from high to low almost immediately, and it holds it in. That's what a flip-flop does, and it's a lovely piece of logic design. Now, these are NAND gates, which is a inverted or not and this here is a 7400 series TTL chip, and it has 4 NAND gates inside it. So what I've done is I've reproduced that logic circuit in here by using the 6 lines on this side of the chip to provide the flip-flop. When I am flipping my hand switch here, I'll go like this. When I flip it up, that signals transition. When I flip it back, that latches the transition. So each time I do this, it's not 2, it's just a single one. So click, click goes high, click, click goes low, click, click goes high, and so on and so on and so on. I'm only saying this just to illustrate it when I start fiddling with it in a second. Now, I mentioned that hand stepping only works with some processors. Most processors use the equivalent or the exact of DRAM inside the processor for holding the register data, the processor status flags, things like that. So these things, DRAM, need to be refreshed. Thus, as we mentioned before, the refresh circuit that makes this so much nicer than the 8080. And if you don't refresh it a certain number of times per second, then it actually loses or degrades what's stored in that register. Thus, most processors have a minimum clock frequency. Now, some of them, older processors like this, can be very slow comparatively to what they're designed for, like a 1 megahertz 6502 might go down as far as, 500 kilohertz or something like that, but anything below that and it starts forgetting what it's doing. This has static RAM for all of those internal registers, so if you hold the clock, it doesn't care. It's going to keep that continuously as long as the chip has voltage applied to it. So this means that we can hand step it like this because it's not going to forget in between. And that is extremely, extremely nice, and yet another reason why I truly love the Z80. Alright, well now I've bored you to tears with the basics. Let's discuss what's actually going to happen. When I plug this in, power circuitry is going to come up, and it's going to start in an unknown state. Now, the resistor here will pull the reset circuit high, which is off, so it's going to run through the reset cycle. Now, it needs to be stepped, clocked through that cycle. Now, because we're hand stepping, it means I'm going to have to... Oh, I bumped you again. I'm going to have to flip this a couple times before the reset cycle completes. These lights may come up in a funny pattern when it first turns on. They may not. But when it first comes up, the pins are all in random, whatever random, sunspot radiations in the chip at the time. So there might be lights on, there might be lights off, but when we flip it a few times, the reset will complete and it will bring it into a known state. It'll clear the address lines, it'll clear the data lines, it'll reset all of the registers, it'll reset the processor flags register, it'll reset the program counter. It should take, I think, 6 clocks to complete the reset. Then, because I said we have these tied, it's going to start seeing no ops. So the first instruction it'll see is a no op. The processor immediately is going to go into a fetch. That's pretty much all it does. Fetch process the instruction, output as necessary, loop and loop and loop. So it's going to start at address 0, it's going to do a memory fetch, it's going to find a no-op, we're going to clock a few more times, it's going to increment the program counter, and it's going to try and pull from memory cell 1, no-op, click, 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 memory cell 2, no-op, click, click, click. So we should see the lights lighting up in order, in binary of course, as it is addressing the subsequent memory locations in what it believes to be the memory chip. It takes, like I said, 2 clicks for every clock transition, and it'll take 2 cycles for every no-op to complete. So it should be 4 clicks before this changes. Alright, so let's plug this in. No lights. Oh, there we go. That should be reset now, I think. Two, 3, 4, 5, 6, and so on. Okay, so now I'm just playing with myself, but you get the point. So what we've got here is an extremely simple counter. I know that's totally brain damaged and you are utterly and completely underwhelmed after I've been rabbiting on for 15 minutes, but it means the processor works, it means it is receiving the no-ops like it's supposed to, and it's incrementing the process counter. It is the start of a computer. Well, okay, the very, very early beginnings of a computer. What comes next? Firstly, we need to be able to have it remember something. It has registers in it, and it is possible to have a running system with just the registers. There are enough in here that you could do some very basic things. Adding some RAM obviously would be a good start. Now, I have some static RAM chips around here somewhere, so I'm going to see if I can find those. That's good, but without a ROM, it's going to be as dumb as a post. We're going to have to manually click in data to it or something like that. That's not much use. Now, I don't actually have any EEPROMs, and worse than that, I don't even have an EEPROM programmer, even if I did have any bloody EEPROMs. I do, however, have some flash RAM. So I think what I'm going to do, probably for the next video, is build a flash ROM programmer. And that way we can load a basic program into the flash ROM, plug the flash ROM into the circuit with the Z80 and the RAM, and get a simple computer. Get it operating some instructions other than no-ops, one would hope. And after that, some kind of way to actually communicate it, which will probably be serial, because with a UART, it's ridiculously simple to add serial, and it totally beats the crap out of trying to add a keyboard or video, which is a whole nother saga, and I don't want to deal with that. In fact, I doubt I'm even vaguely competent to do a video generator, but aside from that, so serial. I could also add some 7-segment displays, and we could have register contents or something like that pop up. I could add buttons so that we could talk to it, maybe a hex keypad. But I think serial sounds like more fun. And again, like I said, with the UART, which is a serial chip, and it does all of the serial in the chip, it makes it really, really easy to add serial. And then with the Max 232, we can bring it from TTL voltages up to RS-232 voltages, and so I can hook it to a dumb terminal or my PC or something like that. Well, that comes next. Hopefully we'll get there soon enough. As I said in the beginning, I really appreciate all you guys keeping up. I'm really excited to have 103 subscribers. I appreciate all of your comments. I know that's a lot of appreciating, but I'm not full of crap. I really do love you guys. I hope you have a great day. Thank you for watching.